Chapter 3. So we want to kind of move along at a little faster clip just because next week we're supposed to be into chapter 4. And I'm like, geez, we haven't even done chapter 3. But chapter 3, it's about how how atoms actually combine to create more stable combinations. I took chapter 3a and chapter 3b and I have combined them into just chapter 3 since I didn't split it in the first exam and second exam. So if you've printed 3a and 3b, we're just going to go from one straight to the other. So they won't look like two different files. So you know that I post these marked up PowerPoints. It'll just say chapter 3 marked up, but it's actually A and B combined, just so that you know. So where are you? So just to back up, remember in chapter 2, stuff we covered in chapter 2, we talked about subatomic particles. No, come back. So subatomic particles, good. To get this down. Protons, neutrons, and electrons. So protons and neutrons, they are where in the atom? Yeah, they're in the nucleus. And what other thing do they have in common? Protons and neutrons have mass. Okay, so that's really like their claim to fame. When you don't have normal numbers of neutrons, you end up with the weird isotope thing, some radioactive, but really protons and neutrons, both of them in the nucleus, and both of them have mass. So that's really the bulk of what we talked about in chapter 2. The third group, though, the electrons. The electrons are really responsible for the interaction between atoms, what causes water to form, sodium chloride to form. The way that you end up with compounds is all because of the electrons that are found outside the nucleus, but they're not random. So they did studies to try and figure out, okay, well, what do these electrons do? And they found out that one, they don't just sit still. Okay, so they move. They're constantly moving. And they move in what was described as a defined path. Well, kind of like the moon orbits the Earth, like the Earth orbits the sun. They said, well, these electrons are in a path and we call them orbitals because it's just a way of trying to describe where they go, how they move. They found that optimally, electrons want to get as close to the nucleus because if they've got to go in a path, the closer they are to the nucleus, the shorter the path. So like if you look at these, so here's like little electron 1 and 2, and there's the nucleus in the very center. So the one that's close, if it goes around in this circle, that's its orbital. But the electron that's further out, it has to go in its path at the same time frame that the smaller one does. So which one has to move faster? Yeah, the one on the outside. So this electron is actually going to have to go faster than the one that's closer in order to make the loop. So they both end up coming back at the exact same time, but this one's going to go slower and that one's going to be much faster. So they found that electrons, the further away they are from the nucleus, the faster they have to go, the higher energy they have. So optimally, would you like to use like max energy or would you like to use as little as possible?
Little as possible.
That's pretty much it. That's so much easier. So they found electrons tend to fill an orbital close to the nucleus, but there's only so many that can fit. So they found that in the closest to the nucleus orbital, only 2 electrons can fit. So I think of it as being like that's just as much as you can put. So when you're looking at an element like hydrogen. So hydrogen is all the way up in the far left. Hydrogen has 1 proton and 1 electron. So its little proton is in the nucleus and its electron is in that first energy level, the one that's in the smaller path, the one that's really close to the nucleus. So what about helium? Next size up, helium has atomic number 2. So that has 2 protons, 2 neutrons. Those are in the nucleus, not such a big deal. It's their 2 electrons. So helium has 2 electrons, and that's going to fill the first energy level. When you have a full energy level, that creates a stable atom. So filling an energy level creates a stable atom. And for the first energy level, it's just 2. But the further out, so the next one, which is like lithium. So lithium is the next element size-wise. Lithium's atomic number 3, has 3 protons, 3 electrons. So only 2 fit in the first. So that means in the next outer shell, you're going to have 1. So lithium, 3 electrons, 3 protons. But those 3 electrons, 2 electrons end up in the first energy level, and 1 electron will be in the second. Because that's going to get them closest to the nucleus, but only 2 fit in the first. Sort of like such a small little orbital, you can't fit any more than that. So what do you think about beryllium? So beryllium's atomic number 4. How many in the first? 2. How many in the second then? The other 2, right? So you're accounting for the number of electrons. Remember, the atomic number tells you the number of protons, but it also tells you the number of electrons. So we know that beryllium, Be, has 2 electrons in the first, 2 electrons in the second. And as you continue across to boron, to carbon, to nitrogen, to oxygen, how many will you always see in the first?
2.
Just 2. And then the remaining electrons will fit into the second. Now the second's bigger. It can hold more than 2. So you can kind of think about it, it's like a bigger path because it's further away from the nucleus. So you can fit more electrons out here. So when you get all the way out to fluorine, this one's the second, fluorine has 9. So in the first you would have 2, in the second, 7. So that would give us our 9 total. The atomic number tells you the total number of electrons. And then the last one, all the way at the end, neon. Neon has an atomic number of 10. So they found that in the first energy level, that's always the same, only 2 fit. But now in the second energy level, they found 8 could fit. 8 in the second energy level creates stability. So it's kind of like there's pairs that oppose each other. So there's a pair here, and a pair here, and a pair here, and a pair here. So they like balance each other. So having 8, other than the first energy level, 8 creates stability. And in fact, all of the elements in that last column, except for helium, they all have 8 in their outer electron level. So the outermost level having 8 is what creates stability. And remember I told you those are the noble gases? Those are the gases that really don't react. They are some of the last ones to be found because they're inert. They're stable all by themselves as atoms. So they tend to not form compounds. They tend to not form bonds with other atoms. They're just perfectly stable as is. So you can kind of, huh?
It's not like a balance thing. The more you can get, the more.
Like a seesaw kind of thing.
Yeah, something like that.
But 2 in that first energy level, because it's so small, 2 is the max. So that creates stability. But beyond that, it's always 8. It's always series of 8, and it's always the outer one. If you can get the outer one to have 8, then it's like they sit and like pair each other off, so they balance each other, and that creates a stable molecule. Okay, so things to remember: electrons are really small, constantly moving. In fact, you really can't say where they are because they never sit still. I just think of them almost like little particles of energy moving really fast. But they have an energy to them, and that's going to keep them in a path. So they move in this orbital path depending on where they sit in the atom. So the energy levels, they're not really like an equal staircase. Some energy levels actually are further away than others in terms of their location. And here's a good way to look at it. So they say, like the first energy level, there's just 2 electrons. And it's really small, like so those electrons move the slowest. But to go to the second energy level is a pretty big jump. But remember that if you can have 8 electrons in the outer energy level, that'll create stability. Then when you get out into the third, it's still the same thing. 8 electrons create stability, even out into the 4th. So they summarize these, and you can actually tell the number of electrons in the outer shell from the periodic table. You don't even have to memorize them. You don't have to remember there's one in the first and two, you don't have to remember that order for the main group elements, which are the majority of the elements that we're going to talk about, the ones that are involved in forming most of your ionic and covalent molecules. The number in front of the capital A tells you the number of electrons in the outermost energy level. All the other inner energy levels are full. It's always the outer one that you're most interested in. They call the outer, yep, all the way at the top. And I specifically use this periodic table because it keeps the capital A. So the first 2 columns and the last 6 columns all have a capital A at the top. Notice they don't have it on this one, but I specifically picked this one because of that. It does have it, so it's easy to tell. They're called the outer electrons. They are in the highest energy level. They call these valence electrons. And if you look at the periodic table, everything in the first column, H, Li, Na, K, Rb, Cz, everything in the first, the alkali metals, they all have 1 electron in their outermost energy level. That 1. So that tells you that there's 1 electron there, whereas everything beryllium, magnesium, calcium, everything in the second column is 2A. That tells you that there's 2 electrons in the outermost energy level. So you don't have to memorize electron configurations. You don't have to memorize where they are. All you have to do is remember on that periodic table, it's always the number in front of the A. So when you go to boron and aluminum, they're in group 3A, so they're going to have carbon and silicon, they're going to have 4. Nitrogen and phosphorus, 5. Each one, it's based on what's in that column. So they wanted a way to depict these valence electrons, and so they came up with what is known as the Lewis dot structure. The Lewis dot structure is just the element with the dot for each valence electron. So if we had hydrogen, how many dots would we put around it? Just 1, right? And same thing with lithium, same thing with sodium, same thing with potassium. You just have the symbol and you just have 1 dot, which just means there's 1 electron. They have other electrons, but those are in inner levels, and those inner levels are stable, they're full. So it's only the outer one that we're really concerned with or interested in. Everything that you see with beryllium, magnesium, and calcium, they're all going to have 2 dots. And I don't care if you put your 2 dots together like a pair or if you spread them out. Does not matter to me. As long as you just put a dot for each of the valence electrons. Calcium, same thing. So the maximum number you're possibly going to put around an element is what? 8, okay? So you may end up with 2 above, 2 below, 2 to the left, 2 to the right. So you could pair them. I tend to spread mine out just so that I can go back and help to link things together and see how they create bonds. So with boron and aluminum, I would spread them out. I would put 1, 2, 3. I don't really care as long as you have 3. But it helps me to see that they're missing some things. Doesn't matter if you put them all on one side. Doesn't matter to me if you have them in like top, bottom, left, or right, or left and right and top or bottom. It doesn't matter the order as long as you have like 3 dots around aluminum, 3 dots around boron. So carbon. Ooh. Say what? Yep, so if you had like, it wouldn't be wrong if you wrote silicon like this. You know, like 2 and 2, pairing them off. The only problem you run into with that is if you're trying to find combinations, it's harder to see that you have unpaired electrons, because ultimately you're going to want to pair them. They're going to want to create 8, because 8 is going to make things stable. Except for hydrogen and helium, 8 is always going to create stability. So that's always sort of the goal. And that's why I always spread mine out. So nitrogen, once you get to having 5, 1, 2, 3, 4, that means now you start pairing them up. So if there's 5 valence electrons, you just make sure you have 5 dots. And it doesn't matter to me where your dots are, just so long as there's a total of 5. Phosphorus has the same. Oxygen and sulfur have 6. That means they'll have 2 pairs that are paired up and 2 that are singlets. And it wouldn't be wrong if you put the pairs on the right and the left, or the pairs on the top and the bottom and the singlets on the other ones. Which one? Here? You could, but but you're trying to make 8. So when you split them out, it helps you to see the ones you're missing, is the way that I always look at it, is by spreading them out. Then I see, well, I'm going to have an electron here and here and here in order to get it to have its 8. So that's why I tend to spread them out. But it really, technically, if I asked you for a Lewis structure and you did 3 pairs, it wouldn't be wrong, as long as you had 6 dots. Okay? 2 above, 2 below, 2 to the left, 2 to the right would be maximums. So fluorine and chlorine, they're like almost there because they have, so there you're going to have 3 pairs. 3 pairs, geez. Nope. 3 pairs that are paired and only 1 single. So there's like only 1 missing. Neon and argon, then, they will have, so they'll have 1, 2, 3, 4, 5, 6, 7, 8. And that's why they're stable. Now, helium is going to have just 2, but it's only got the first energy level. So for helium, 2 is stable. Helium only needs 2 because it's that first energy level that's so small, so 2 is really the maximum. So that one would only ever have, you wouldn't ever have 8 in helium because it won't fit in that tiny energy level. But all the other noble gases are always going to try to have 8. So like I said, you don't have to memorize that. All you have to do is remember the number in front of the capital A for the first 2 groups and the last 6, it tells you the number of valence electrons. And you can describe or draw the valence electrons using the Lewis dot structure. So another big thing in trying to figure out how compounds form, there's the dots, is that zigzag line. And again, I picked this periodic table because it has a really nice defined zigzag line. Whereas again, if you look at that one over there, you're like, man, I don't know where it is. Okay? But here you can see this dark line because everything that is to the left of the zigzag line is all the blue, metal. All the yellow, non-metals. Okay? So that is another way of being able to automatically look at a compound and determine what type of bonding occurs. Everything over here, metals. Everything to the left of the zigzag line is a metal. Everything to the right, non-metal. So metals tend to have few valence electrons. Like sodium, it only has 1. Calcium, it only has 2. So for those to be stable, they're going to need 8. So they don't have very many. They need a lot in order to create stability. And that's really typical. Metals, they have few valence electrons. They need a lot. But what about nonmetals? What about like oxygen and fluorine? So like oxygen, how many valence electrons? 6. Sounds group 6A. So it only needs 2 to create stability. Chlorine, it's in group 7. It only needs 1. So nonmetals have a lot of valence electrons. They're much closer to being full. So they have an almost full number of electrons. This difference creates the first type of bonding. So this difference to create stability is only seen between metals and nonmetals. And you can always tell, because all you do is look at the periodic table. If you see that the first element is on the left side of the zigzag line, the second element is on the right, then you know it's this type of bond. It is called an ionic bond. So something you're very familiar with, table salt. Table salt is formed by the formation of an ionic bond. So sodium exists just with 1 electron. As a pure element, it exists with just that 1 electron. So it either needs to get 7 or it could get rid of its 1. So if you had a set of 8 and you're like, well, I got 1. Time goes by, are you really going to continue looking for it? Continue trying to find the rest of the pieces. That's going to be a lot more difficult. Chlorine, on the other hand, is in group 7. So you see it's got the 7 dots. So it only has this 1 empty spot. So if it could find just 1 electron, that's going to create stability. So chlorine has this pull. Sodium just sort of has this 1. Since it's only 1, if it gets rid of it, so sodium has 11 protons and 11 electrons. If it gets rid of an electron, how many electrons will it have now? 10. So what element has 10 electrons? Neon. And neon is a? But it's in that column, it's a noble gas. It will have an electron configuration like a noble gas. We said noble gases are stable. So if it can have that stable octet, it loses its outer electron and the next level down has 8. So it creates that stability by getting rid of that electron. It still has 11 protons though, because if it lost a proton, then it wouldn't be sodium anymore. So it doesn't lose protons, it loses an electron. That electron gets transferred. So the sodium loses it, the chlorine pulls it in. So chlorine started off with 17 protons and 17 electrons. And if it gains an electron, now it has gained one, 18. So find element 18. It's argon, another noble gas, another stable element. So if chlorine can only gain 1, it's going to have an electron configuration like argon. It's going to be stable. So if you had the two, so sodium, if you had pure sodium metal, you actually have to store it under kerosene. It is reactive with oxygen in the air. It would become sodium oxide. It would grab oxygen molecules out of the air. If you took sodium metal and you threw it in water, it would generate so much heat, it would explode, like bounce across the surface of water. Very reactive. What do you know about chlorine? If you inhale chlorine gas, it's not healthy. It's kind of toxic. So you have these two atoms in and of themselves, super reactive. You can't come in contact with, but if you put them together, the sodium gives its electrons to the chlorine, and what are you left with? A pile of what? Table salt, right? So you're left with table salt, which is like a flavoring that you put on your food. So we eat it all the time. So it's not something that then is super reactive because we've converted the sodium to an ion. Sodium has lost an electron and become positively charged. Chlorine has gained an electron, become negatively charged, but that gives them an electron configuration like a noble gas. And that creates stability. So this is table salt. Yeah, so the atoms in and of themselves, individually as a pure element, extremely reactive. But if you combine them, they can swap electrons to create a very stable arrangement. So the sodium and the chlorine, now that they're ions, they have unequal numbers of protons and electrons. So that means that they have a charge. So an ion is just an atom that has lost or gained electrons and now has a charge. The anion, which is what chlorine is, this is a negatively charged atom. It has one more or more electrons than protons. So it has a negative charge. It has more negative electrons than positive protons. So Cl always has a minus. And they call those anions. Another thing that you can always say when you have this ionic compound, the nonmetals always gain electrons because nonmetals are close to being a full set and they're always going to want to pull electrons towards them. So nonmetals gain electrons when you form an ionic compound. Sodium, the metal, it's going to lose its electron, so it ends up having one less electron than proton, and it is called a cation. So cations are positively charged atoms. And if you look at the number, they'll always have more protons than electrons. These lose. Metals will lose electrons in order to create a stable electron number. And they end up with more protons than electrons, which is why they end up with that positive charge. Correct, because the electrons are negative. Correct. Just think about it. You're gaining you're either gaining negative, which makes you negatively charged, or you lose negative, which means you have more positive protons than negative electrons. So in this, so the metal is always going to lose its electrons, and so therefore it's going to have more protons than electrons, and that's why it has that positive charge. It'll end up with more positives than negatives. And so that's what the cation is. And metals do this. So again, on the periodic table, if you see two on opposite sides, you know it's an ionic compound, and you know that these are always going to lose electrons. Metals will always lose them because they don't have very many. They can lose their 1, 2, or 3 electrons. They'll become positively charged, but then they become like noble gases. So they become much more stable. Okay, so we can actually apply this as like a rule. When you have a metal and a nonmetal, you'll have an ionic compound. When you write it, will you put the metal first or the nonmetal? You always put the metal first, right? Like sodium chloride. So that's like the best example, NaCl. You always put the metal first, the nonmetal goes second. Now the ratio of metals and nonmetals, sometimes you have to figure it out. But this one's really pretty straightforward because you know that sodium is in group what? 1. So you know that sodium's going to end up with a plus charge. So the number of electrons tells you the charge. So for the cations, the group number tells you the charge, and it's going to have a positive charge. Now chlorine's in group 7, so really it's 8 minus the group number tells you how many electrons it'll gain. So you know that chlorine will gain, so it would be 8 minus 1, so it's going to be a negative. And so you can see that you have 1 positive per 1 negative, so the ratio is that you have 1 sodium per 1 chlorine and sodium chloride. But what if we have this, magnesium and chlorine? So where's magnesium? What group? It's in group 2. So that means magnesium has to lose 2 electrons to be stable. You see that you have magnesium over here, chlorine over here, so you know that this is ionic. So the metal always becomes positively charged. It loses its group number. Okay, so it becomes a +2. But the chlorine, we said, is negative. So if magnesium's a +2 and chlorine's a negative, what ratio will they react in? You can figure this out. The number on the metal tells you the nonmetal subscript. So it tells you how many nonmetals in the formula. The number on the nonmetal tells you the subscript of the number of magnesium or metal atoms. So this one, +2 on the magnesium, tells you that you have 2 chlorines. The -1 on the chlorine tells you that you only need 1 magnesium. So it tells you the formula. You can work the formula out by looking at what the charge is and just swap them. I always think of swap the charges. Whatever the charge on the metal, that tells you how many non-metal atoms in the formula. Whatever the charge on the non-metal tells you the number of metal atoms. Let's do a couple more. What if you have K and O, potassium and oxygen? So find potassium. Craning your neck. So it is a plus. And oxygen 6, to figure out its charge, it's 8 minus 6, so that would be -2. So they're not exactly the same. If they were both the same, then it's 1 and 1, right? Then there would be 1 metal and 1 nonmetal, like sodium chloride. But this one, it's not. So in order to figure out how many potassiums in that, this tells you the number of potassium. This tells you the number of oxygen. So the formula would be K2O. So just assign the charge on the metal, charge on the nonmetal, and then just swap them so the charges tell you how many of each you would have. Last thing about this is naming. So how do you name NaCl? How do you say it? Okay, so everybody knows that, right? Okay, so you would say then the metal, you use the whole name of the metal, like sodium. So Cl is chlorine. But you don't say sodium chlorine, you say you say chloride. So you use the first part of the nonmetal plus IDE. So you put that IDE at the end, that's the indication of the compound. So you use the first part of the nonmetal plus IDE. So this one, yeah. And then this one, yeah. Okay, so in the nonmetal group, nitrogen becomes nitride, oxygen becomes oxide, fluorine becomes fluoride. Phosphorus becomes phosphide. Sulfur is sulfide. Chlorine becomes chloride. Bromine would be bromide. And iodine, iodide. Okay, so all you're doing is you're taking like the first syllable of the nonmetal plus IDE. And that's always the same. So it's always the same with the ionic compounds.
So where did you get the two?
Which two?
On oxygen.
Okay, so if you look on the periodic table, so you see it's in group 6. So the rule up there to figure out the charge, you take 8 minus the group number. Okay, so it's really thinking like how many electrons to make 8. So if I'm in group 6, I gotta gain 2 in order to make that 8. So that's how you figure out the charge. How many electrons to make a total of 8. Okay, all right, so let's do some more. So here's another example, and this is when they use aluminum, okay? Even though aluminum is kind of like a metal-metalloid kind of split, but it acts as a metal. So aluminum, though, if you look at what groups it in, when you look up there, you're like 13. Look on the periodic table because it's the number in front of the A, okay? So that one is 3A. So it's going to act like a metal, so that means that it's going to have a +3 charge. Okay, it's to the left of the zigzag line. It'll act like a metal. It'll have a +3 charge. But we said oxygen's in group 6. So to make 8, it's going to have a -2 charge. So the charge on each ion, you do the swap, and that tells you the ratio. So you have to have 3 oxygens and 2 aluminums in order to have an equal transfer of electrons from metal to non-metal and give you a neutral ionic compound. So it's just the easiest way, is just assign their charges and then just do the swap. Now what if, okay, so like this, bromine and calcium. So look at bromine and calcium. First thing to do is you want to, I say, okay, look and see, do you have a metal and a non-metal, yes or no? Find bromine and find calcium. Are they on opposite sides of the zigzag line? Yes. Then you know it's ionic. Okay? So if your 2 elements are on opposite sides of the zigzag line, you have a metal and a non-metal, you know they're ionic. 2, put the metal first. So even though I have them written this way, which goes first? So calcium needs to be written first. Okay? Because calcium's to the left of the zigzag line, it's the metal. Bromine is going to get written second. Next one. Give them the charge. You know the metal will become positively charged. Positive what? 2. Because it's in group 2. So for the metal, the charge is its group number. But for the non-metal, it's going to gain electrons. So you have to figure out how many will it gain to make 8. So bromine is going to be a negative. Because bromine's in group 7, it's going to gain 1 electron in order to make its 8. And then swap. So what's the formula? Yep, so Ca, Br2, take the charges, swap them, and that tells you the ratio. 1 calcium to 2 bromines. It takes 2 bromines to collect the calcium's electrons, is really what that's saying. And then the name, whole name of the metal? Yeah, first part of the non-metal plus the IDE. What about this one? Okay. Right, so it'd be a, okay, so you see, so magnesium's in group 2, oxygen's in group 6, magnesium's a +2, oxygen will be a -2, it's what it needs to make its 8. So when I swap, kind of like balancing equations, if you have 2 numbers that you can divide by, simplify. Okay, so what is the simplest ratio? Yeah, just 1 and 1. So the simplest ratio would be 1 to 1. 1 magnesium can react with 1 oxygen. So if you have 2 even numbers, then you would want to simplify it. I heard the magnesium. What was the second part? Oxide. Very good. This one is bromide. So what would you call that one? I think we've done all the ones above. K is potassium, not nitrate. Nitride, right? Because remember, it's the IDE on the end. Nitrate is next. We're not quite there. Like, and you'll see the difference for the name, but this is potassium nitride. Sodium chloride, magnesium oxide, calcium chloride. But of course, there has to be some oddballs. So in the main group, that number in front of the capital A tells you the number of valence electrons. Really makes it kind of simple to figure out this ratio. It's the ones that are in here. The ones that are in here, the ones that are kind of in that dropped down group, notice they don't have a capital A in front. They have a B, okay? They call those transition metals. They are transition, and the ones that you need to be able to remember are just these three. Okay, we're really not going to use the other ones, but we will actually talk about iron later and chromium and talk about like charges. So that's really why I want you to like get these three. So chromium, Cr, that was one of your 30 to learn. Fe, some people forgot that one, that's iron. And then Cu, that's copper. They're in this transition group, and they're a little strange because instead of being able to just lose a specific amount, they can create stability and lose varying amounts of electrons. So chromium can lose 2 electrons and be stable, or it can lose 3 electrons and be stable. So it doesn't really fit the normal stable. Everything likes to have 8 to be stable. These ones are a little odd, but chromium can lose 2 electrons or it can lose 3 electrons. So you can have, if you have chromium with chlorine, that means when you look at this one, you know that chlorine has what charge? Chlorine. It's a -1, right? Chlorine is always going to have a negative charge, and there's 2 of them. So you see that, that's not really right. It's hard to see it. It's got a negative charge, and that's 2. So that would give me like a total of a -2 in this molecule. So that means that the chromium must be what? A +2. Okay, so it's kind of like you could do a reverse swap to be able to figure that out. So the 2 on the chlorine tells you the charge on the chromium. The thing is you could also have this. And so in that, chlorine's still going to have its negative charge, but that now tells you that the chromium must be a plus what? It has to have a +3 because the total number of charges between the metal and the non-metal end up kind of canceling each other out. 3 negative chlorines balances the 1 +3 chromium. So, so just these 3, you can have these differences. So what would you call this? Same way we'd named it before. It'd be what? Chromium chloride. Chloride. And this one too, yeah? So then came the question, well, how do we tell them apart? If we just say chromium chloride, people will be like, well, which one? The +2 or the +3? Which chromium are you talking about? And so this is where they came up with a Roman numeral. So the Roman numeral, if you've ever seen molecules drawn this way or written out this way, that Roman numeral tells you the charge on the metal.
So it has to go after the metal?
And it like goes right in the middle because it's telling you chromium with a +2 or chromium with a +3. So the Roman numeral tells you what the charge is on the metal.
It just has a 1 charge? Do you have to put the 1 Roman numeral?
Because otherwise you still wouldn't know. Like, so you're thinking like copper. So we could have, we could have CuO or we could have Cu2O. So what's on the copper in the first one? So you look at it like, So figure out the oxygen's charge first, because that you know. Charge on the oxygen is 6, so it would be a -2. How many? It needs to be 8. And I don't care if you put 2- or -2. I'm really bad about putting the negative in front. Like, you see how I have -2, but your book says 2-. Okay? Just make sure that you have the charge. Okay? Doesn't matter of which order you put them in. But if you know that there's 1 copper, to one oxygen, and the oxygen has a -2, then the copper has to be +2. Right? They've got to balance each other. The total number of positive has to equal the total number of negative. So what's the ratio? It's 1 to 1, the simplest ratio. So it's in the simplest ratio. So if you had to say its name, you would call it?
Copper 1 oxide.
Would it be copper 1?
Copper 2.
Copper 2. Even though there's only one copper, it's got a +2. So the Roman numeral doesn't tell you how many of them. The Roman numeral tells you the charge. So that would be called copper 2 oxide. What about the bottom one? So again, you know the oxygen's still the same. So you think, so the Cu2 would be, it needs to have a total charge of +2, but I got 2 of them. So its charge would be just a positive. And so in this one, can you see how that's like a reverse swap? The numbers down at the bottom tell you how the charges are at the top. So we took the charges and we could figure out the formula from the charges, but in this one you can kind of go backwards. So you can see that the 2 from the copper is the -2 on the oxygen. The 1 on the oxygen tells you the positive of the copper. Since it's a positive charge, you call it copper 1 oxide. Does not mean there's only one copper. It means you have a copper with a +1 charge. Okay? So just remember that that's what this is telling you. So we'll do a couple more of those too, and we'll include iron next time. But this is kind of the one of the oddballs. You know how English has oddballs? Chemistry has oddballs too. And that's the transition metals. They don't have a specific number of electrons they have to lose to create stability. So they can like form different charges. One more, and then I'll like let you stop. Okay, so in this one, iron 2 sulfide, iron 3 sulfide. If you're given the name, you can figure out what the formula is. So iron is what? Fe. Sulfide is S. So we know it's an FeS. Iron 2 tells you what about the iron? That it's a +2. So remember that the Roman numeral tells you the charge. So this tells me the charge. And then sulfur, find it. It's got a -2 charge. And so if one has a +2, one has a -2, then the ratio is FeS. That is iron 2 sulfide. So in that one, from the name, we can work out the formula. Now if it's iron 3 sulfide, still FeS. The sulfur is still going to have a -2 because it doesn't vary. But the iron is +3. So it's iron 3. So this is the +3. That Roman numeral, the Roman numeral tells you you're going to have an iron with a +3 charge. So now this one's not 1 to 1. What would this formula be? Fe what? Do the swap. Fe2. S. 3. So the charge becomes the ratio. Unless they're equal, then just simplify. Like the top one, the charge was 2 and 2, so you would just simplify to a 1 to 1 ratio. But the bottom one, it's a 3 and a 2. So just take those and swap them, and that tells you the formula. This always works with ionic compounds. You can go from names to formulas. You can go from formulas to names. You can figure out what the charge is just from looking at the periodic table. Your metals are always going to be positive by their group number. Your nonmetals are going to be negative based on how many they need to make 8. Transition metals, the oddballs, just these 3. Copper, iron, and chromium. And remember that Roman numeral tells you the charge. not the number of them. It tells you the charge, and you can work your way to figuring out how many based on that charge. So there's one more weird one. And these are where we came up with these weird nitrates. Okay? So they found that there's groups of atoms that together have a charge. These groups of atoms, like this, NH4 plus. So the nitrogen and 4 hydrogens together have a positive charge as a whole. So you may have noticed this in some of our balancing equations. So like we had in some of the balancing equations, we had like K3PO4. That PO4, that's a polyatomic ion. NH4 plus is a polyatomic ion. These are listed in your book. Polyatomic ions are in chapter 3.
Page 81.
82 on mine. Yeah, so it's table 3.2. Yeah. I was like, oh no. I was like, did they change page numbers on me? I thought I was worried for a minute there. Okay, and so this is the chart. It's table 3.2, common polyatomics. The only ones that I want you to learn are the ones that are in boxes, plus those. Okay, so the OH. So it's an oxygen and a hydrogen together has a negative charge. And so they don't call it oxygen hydride or anything. It's called the hydroxide. So that's a hydroxide ion. It has a -1 charge always. NH4 plus is the only positively charged polyatomic ion on the list, and it's called the ammonium ion. The other ones are all some version of an oxygen nonmetal. So we have NO3, which has a negative charge. That is the nitrate. You have ClO3, negative. That is the chlorate. CO3, which is a 2- charge. That's the carbonate. SO4, 2-, that is the sulfate. And the last one is the PO4, 3-. It's actually got a -3 charge. And that's the phosphate. So when you have these, ammonium will be the only one that's out front because it's positively charged, so it's written like it's a metal. So it'll be out in the front of a formula. All of the other ones you'll always see like as the second part. They act like non-metals, so they're going to be the second in an ionic compound. So you can have something like this. So magnesium and the hydroxide ion come together. The hydroxide ion is a negative charge. The magnesium is a +2 charge. So do you see how you swap those in order to get the formula? When you say its name, whole name of the first, and then the name of the polyatomic. So you don't change the end, so it's just magnesium hydroxide. This is one we've used in lab. So what's it called? It's sodium hydroxide. So it's kind of like lye. It's a really strong base. The number of the polyatomics. So that top one, because I have 2 hydroxides, I had to use those parentheses. Remember in balancing equations, you had things that would be in parentheses? That's why. There were always SO4s or PO4s or something like that. If you look back at your periodic table, I mean, back at your balancing equation sheets, you should now like see, oh look, those are all those polyatomic ions. Those are all the ones that were put in parentheses because they kind of exist like a group. So they exist all on their own. They tend not to split off and go in their separate directions. So what would happen if I took Na and CO3? What would be the ratio that they would exist in? So Na would have a what? It's +1. It's in group 1, right? So you know that Na would have a +1 charge. It's in group 1A. It's a metal. And CO3, you can see it has a -2. So in order to figure out their ratio, you would flip them. So Na, you have to have 2 of them. CO3, you only have to have 1. If you only have 1, you don't have to put a parentheses. You only have to do the parentheses on the polyatomics if you have multiples. So in naming, it's sodium carbonate. Whole name of the first, and then the name of the polyatomic. So always use the whole name of the first. So what about this one? So if I have lithium and the phosphate come together, what's the charge on the lithium? Plus what? +1. And the phosphate is a -3. And those are ones like you either got to put them on your card so that you can remember them, okay, or commit them to memory 1. And these really are like the most common ones. The only other one that's really common is the bicarb ion, that HCO3, but it's similar. That's really the only other one. But I just use these 7 and we really stick to these for the most part. So in order to figure out the ratio of lithium to phosphate, it would be the 3 of the phosphate charge becomes the number of lithium. Charge on the lithium tells you the number of phosphates. So it would be Li3PO4 and its name?
Lithium phosphate.
Use the whole name of the metal and just the name of the polyatomic after.
So if you had to change phosphate, would it be in parentheses with the charge at the bottom you change it to? So
Yep, the charge outside.
Outside.
See, like MgOH2 in the upper, you put the parentheses and you put the number that was the charge. The magnesium charge tells you the number of hydroxides. So you'll have that parentheses with the 2 outside. So that tells you like 2 OHs, 2 hydroxides. So this is lithium phosphate. Where are you? No. Oh, well, here. Let me just do. I need. I don't want to talk about ions. That's too much. We're going to put a new slide in. Blank. Because it's just easier. I thought I had made a list. So let me give you a list. So if we have calcium and nitrogen, tell me what the formula would be and what would be the name. So the first one's pretty straightforward. So calcium and nitrogen, when they combine, how do you figure out the formula? Nitrogen is -3. See, it's in group 5. That means it's going to have to gain 3 to make 8. So remember, non-metals 8 minus the group number tells you the negative charge. So now you just take these end. Exactly. And the name? Calcium nitride. Yes? Very straightforward with that one because you got a metal and a non-metal. Just assign their charges, swap them, make sure you have the simplest possible number. This one is 3 and 2. You can't simplify that anymore. Always whole name of the metal, first part of the non-metal, plus IDE, calcium nitride. Now this one, stinking iron. So when you look at iron, you see that it's down in that lower group, so you know that that's an oddball, okay? So you don't automatically know the charge, but what do you know about the phosphorus? Phosphorus is -3. So notice that the phosphorus is a -3 and the iron has a 3. So it looks like they're on opposite sides. So what does that tell you about the charge on the iron? It's got to be a +2. So you see in that one, I took the subscripts. I took the number of each element, and that tells me the charge. It kind of did like the opposite of the first one. The first one, I assigned charge and swapped to figure out the ratio. Second one, look at the ratio, swap them back, and that'll help you to figure out the charge. Okay, so it still is Fe3P2, but how would I name this? Phos, huh? Nope. Ide, right? Unless the only time an 8 means it's a polyatomic. So you don't see any oxygen after that phosphorus. It's just the P all by itself. So that is phosphide. And the 2 tells you that the iron's a +2 charge. So the Roman numeral tells you the charge. So about this one, Mg and SO4. SO4. Nope, they're both together. So this is a group, is the it's a -2. It's the sulfate ion. Okay, so look back at that list that we just did. The sulfate ion is SO4, always has a -2 charge. So this, what's the formula? Stays the same, doesn't change because it's a +2 and a -2, simplest ratio. They're not going to change. 1 magnesium to 1 sulfate ion. And you would call this? Yep, mag sulfate. Have you ever had a colonoscopy? Sodium citrate, magnesium sulfate.
Why don't you write the numeral for that one?
Because it doesn't change. The magnesium's only going to have a +2 charge, right? So copper, chromium, and iron are the only ones you have to worry about the Roman numeral. Okay? Those three are the only ones, and it's because they're in that transition group. So they're in this group. And so they have variable numbers of electrons they can lose, so they could make different ions. So there's more than one possible ion. But really, those are the only three. But we will talk about them again. So that's why I cover it. Okay, NH4F. F is a minus, and NH4 is positive. Okay, so you see in this one, it's a 1-to-1, so you don't have to change anything. So its formula is exactly the same, but you still put NH4 first, even though it's the polyatomic, because it's the positive charge. So typically those polyatomics come at the end, but the ammonium's a positive charge like metals are, and that's why it gets listed first. And you would call it ammonium who? Fluoride. And it's FLUOR because otherwise it's flour. That's a common misspelling. I know there were some people that had problems with phosphorus. There was like phosphorus. Well, they're rhinoceros. Okay, so what about if you're given the name and we got to go to the formula from there? So copper is what? What's its elements or symbol? Cu. And so if you see it's copper 2, that tells you it's a positive what? So the Roman numeral tells you the charge. So you can just go ahead and write it right down. And then nitride. So what's a nitride?
5, so it's -3.
Okay, and its symbol? Yeah, just N. Right? Find the N. It's not nitrate, it's a nitride, so it's just nitrogen. I don't want you to and that's a problem. Sometimes people see nitrate and they just want to put a nitrogen, or if they see a nitrogen, they go, oh, that's a nitrate. Nitrates is an NO3. So it's a nitrogen with 3 oxygens and has a charge as a whole. If you see nitride, that's just a nitrogen. So this one, what are you going to do to figure out their ratio? Yep, so swap them. So that means we have Cu, 3, N, 2. And that's the simplest ratio, a 3-to-2. Potassium sulfide. So potassium is what? K. So you see that it's in group 1. Sulfide is?
6 is -2.
So then you do the swap them. So it would be the formula K2S. So this pretty simple. If it's a metal and a non-metal, assign their charges, just swap them. That tells you what the formula would be. Always make sure the metal's written first, then the non-metal. So one last one, then we'll quit. Aluminum carbonate. So what goes first? Which is Al, and it's +3. So see that it's in group 3A, and it's below the zigzag line, so it's a +3. Carbonate is, so it's a CO3. Find the carbonate. It's a polyatomic ion. So when you see these 8s, then you're looking for the polyatomic, okay? But if you see an ide, then you know it's just the element. How are you going to figure out the ratio? Swap them. So you would end up with Al2, then what do I have to do? Parentheses, right? Put the parentheses. So you're really saying it's 3 CO3s. So that's the reason for the parentheses. But it's just swapping them. So if you're going to do a polyatomic from that, okay? So that's really as hard as ionic compounds go. That's the worst of it. Okay, so next time we'll start off talking a little bit about these ionic compounds and what they end up doing in your body. And then we're going to go on and talk about covalent so that we can go ahead and finish this chapter up.
You want us to keep our test?
Yes. So I'll tell you just to make sure. So you keep your test all semester. You're going to turn them all back in when you take your final. Okay? So you need to put it someplace you don't lose it. 15% of your questions on your final are on that test. Okay? And I'll tell you, it's the ones you missed. Like I specifically go through my key and I'm like, oh, 12 people missed question 3. Let's put that on the final. Oh, 9 people missed question 7. Put that one on the final. So it's the most like, I've had people get 100 on a final and I've had people get a 15 on a final. So you really want to go back and look at the ones you missed. Okay? I really want you to look at your test and decide, why did I miss this question? Did I not study it enough? Did I read it wrong? Did I not write enough on my little note card? Okay, because you have a note card, so you could have like put things in there. A lot of people didn't fill their note card. I had people that had like a third of their note card done. And so I was like, yeah, you had a lot of extra space. You could have added more to kind of clue you in to help, okay, look for this. When you see this, do that. Okay, so that's kind of, start thinking about it because you're going to be able to use another note card for this one. So you might want to start thinking about, how do I identify Ionic? How do I go about naming? What's that Roman numeral mean? Like, and maybe even putting examples, like start trying to condense that information so that as you start to like design your note card for the next one, you can start doing that straight away with these. You can now do the dynamic study modules for simple ionic compounds, and you can also do like the whole first half of chapter 3's homework. Okay? So we will pick up and talk more about this next week. I was like, when?